1. CERN breakthrough, first evidence of CP violation in baryons. 2. Unraveling the antimatter mystery, why does matter dominate the universe? 1. CERN breakthrough, first evidence of CP violation in baryons. Picture this, our universe shouldn't exist. During the Big Bang, matter and antimatter should have completely annihilated each other, yet here we are in a cosmos dominated by matter. The solution to this existential riddle might lie in a fundamental cosmic imbalance called CP violation. And now, in a physics first, scientists at CERN's LHCb experiment have detected this phenomenon in baryons, the very particles that make up your body and everything we touch. But here's where it gets controversial. What they found aligns perfectly with our current physics theories, even though those same theories can't explain our matter-dominated universe. Let's unpack this step by step for clarity. Current cosmology tells us the Big Bang created equal amounts of matter and antimatter. When these opposites meet, they annihilate in bursts of energy. Yet somehow, a tiny fraction of matter survived, about 1 particle per billion annihilations. This survival mystery remains unsolved by our best particle physics framework, the Standard Model. The plot thickens with CP symmetry. CP combines charge, C, and parity, P, symmetry. Charge symmetry means physical laws shouldn't care if you swap particles with antiparticles. Parity symmetry suggests physics works identically in mirror-image universes. Back in 1964, physicists James Cronin and Valentine Fitch shattered this assumption by observing CP violation in decaying neutral K-mesons, particles made of quark-antiquark pairs. Their Nobel-winning discovery proved matter and antimatter could behave differently. Soviet physicist Andrei Sakharov later proposed that amplified CP violation in the early universe could explain our matter surplus. Since then, CP violation became embedded in the Standard Model through the Kabibo-Kobayashi-Moskawa (CKM) matrix, a mathematical menu describing how quarks transform via weak nuclear force interactions. But there's a massive problem. The CKM matrix predicts CP violation effects far too weak to create our universe. As Peking University physicist Xiuting Yang explains, Big Bang models require about 1 surviving baryon per 10 billion photons, while Standard Model predictions only achieve 1 per quintillion photons. That's like needing a bucket of water but having just a single droplet. Even more puzzling? Until now, CP violation had only been seen in mesons, not in baryons, the heavyweights like protons and neutrons that constitute 99% of visible matter. Theorists struggled to predict baryon behavior due to complex strong nuclear force interactions. This gap left room for speculation. Could baryonic CP violation differ from theory and explain our universe? Q CERN's groundbreaking study. The LHCb team analyzed beauty baryons, containing up, down, and beauty quarks, and their antimatter counterparts produced in LHC collisions. They tracked decays where baryons became protons, positive K-mesons, and pion pairs, while antibaryons decayed into antiprotons, negative K-mesons, and pions. CP violation would create an asymmetry between these decay rates. The verdict? They observed a clear imbalance at 5.2 sigma significance, way beyond statistical fluke territory. Here's the twist, the result matches Standard Model predictions. Yang notes this experimental precision actually surpasses theoretical calculations. Other decay channels showed no CP violation, but that's likely due to insufficient data. So what does this mean? The Standard Model passes another test, but our cosmic matter mystery deepens. Current extensions to the model, like those involving dark matter or new particles, aren't ruled out, they simply lack precise predictions for baryonic CP violation. With the LHC's third run underway, scientists hope to study decay intermediates, potentially constraining new theories. University of Hawaii physicist Tom Browder calls it an important paper that introduces an old type of CP violation in a new system. Theorists will now scramble to interpret these findings within, or beyond, the Standard Model. Now, let's tackle the elephant in the room. why does this matter? If the standard model can't produce enough CP violation to create our universe, yet keeps passing experimental tests, are we missing something fundamental? Could dark matter interactions, like those proposed by the late and Nelson, hold answers? Or does this suggest an entirely new direction for physics? What's your take? Do you believe extensions to the standard model will solve the matter-antimatter puzzle, or are we facing a more profound paradigm shift? Share your perspective below. 2. Unraveling the antimatter mystery. Why does matter dominate the universe? What lies behind the universe's enigmatic relationship with antimatter? Let's dive into this captivating mystery. The background: on July 16, a groundbreaking announcement emerged from a collaborative effort of scientists in Europe. For the very first time, they reported a significant finding: the decay rates of matter and antimatter versions of a subatomic particle known as a baryon differ. This discovery sheds light on a crucial aspect of why our universe is predominantly composed of matter. The matter-antimatter dilemma. The Big Bang, which occurred approximately 13.8 billion years ago, was expected to generate equal quantities of matter and antimatter. However, as we observe the cosmos today, it is overwhelmingly filled with matter. Think of the stars, planets, and even ourselves, while antimatter appears to be nearly absent. This imbalance presents one of the most perplexing puzzles in modern science. Physicists theorize that subtle distinctions in the behavior of matter and antimatter, particularly a phenomenon known as CP violation, could provide vital insights into this disparity. Understanding CP violation. CP stands for charge conjugation, C, and parity, P. Charge conjugation involves swapping a particle with its antiparticle, which possesses an opposite electric charge, while parity refers to flipping spatial dimensions, akin to viewing a reflection in a mirror. If the universe treated matter and antimatter identically, we would observe CP symmetry, meaning that even after swapping particles and flipping dimensions, their behaviors would remain unchanged. However, experimental evidence indicates that this symmetry can indeed be broken, a phenomenon referred to as CP violation. The importance of CP violation. CP violation is essential because it is one of the necessary conditions for a universe to have a surplus of matter over antimatter. Previous observations of CP violation. While CP violation has been documented in mesons, particles composed of quark-antiquark pairs, it had never been observed in baryons, which are three-quark particles like protons and neutrons that make up the majority of the visible universe, explained Meenakshi Nayak, an experimental high-energy physicist at the Indian Institute of Science in Bengaluru. The recent findings mark the first instance of CP violation being observed in baryon decays, specifically in a particle known as the λb0 baryon. What is the λb0 baryon? The λb0 baryon is a substantial subatomic particle formed from three quarks, an up quark, a down quark, and a bottom quark. Its antiparticle, the λb0 bar, contains the corresponding antiquarks. In this study, researchers examined how the λb0 baryon decays into a proton, a negatively charged kaon, and two pions, one positive and one negative. They also analyzed the decay of the antiparticle, but with reversed charges. Observing particle decays. This experiment was conducted at the Large Hadron Collider, LHC, in Europe, with data collected by the LHCb detector. Over several years, the team gathered data from billions of proton-proton collisions, which occasionally produced λb0 and λb0 bar baryons. Advanced algorithms and machine learning techniques were employed to identify the rare instances where these baryons decayed into the specific particles of interest. The critical aspect of this research involved comparing the decay rates of the λb0 baryon to its antiparticle. If the laws of physics treated matter and antimatter equally, these rates would align. Any observed difference, after accounting for potential experimental biases, would serve as evidence of CP violation. The researchers calculated a value known as CP asymmetry, which represents the difference in decay rates divided by the total number of decays. Ensuring accurate measurements. The researchers took great care to identify and eliminate other factors that could mimic CP violation. For instance, the LHC might produce slightly more λb0 baryons than λb0 bar antibaryons, or the LHCb detector might have a bias towards detecting one type over the other. To address these potential biases, the team utilized a control channel, a similar decay where no CP violation is anticipated. By measuring any asymmetry in this control channel, they could subtract these extraneous effects and isolate the genuine CP violation signal. Key findings. The researchers discovered a notable difference in decay rates. The CP asymmetry was measured at approximately 2.45%, with a minimal margin of error. Statistically, the measured CP asymmetry deviates from 0 by 5.2 standard deviations, exceeding the 5 sigma threshold necessary to declare a discovery in particle physics, stated Dr. Nayak. This landmark discovery has the potential to enhance our understanding of the matter-antimatter imbalance. While this represents a significant advancement, the observed level of CP violation remains insufficient to fully account for the vast disparity between matter and antimatter in the universe. Scientists are now poised to investigate CP violation in other baryon decays and strive for more precise measurements. Theoretically, they aim to comprehend the intricate dynamics that give rise to these effects and search for indications of previously unknown particles and forces, all in an effort to fill the gaps in our understanding of the universe. The ultimate objective is to determine whether additional sources of CP violation exist that could elucidate matter's predominance. This discovery also touches on a fundamental question regarding our existence: why is there something rather than nothing? Every atom in your body and every star in the cosmos exists because matter triumphed over antimatter. By uncovering the subtle distinctions in how nature interacts with matter and antimatter, scientists are gradually piecing together the narrative of how our universe came to be as it is.